I want to talk today about friction on a horizontal surface. Let's say you have an object on a horizontal surface. The mass of the object is m, which means its weight is m multiplied by g, g being the acceleration of gravity. And we have the normal force. The object is obviously not moving. If the object is initially at rest, it stays at rest. So if I say at the beginning that I have the object there and not moving, it will not start to move unless I apply a force. That is Newton's first law. I'm choosing an appropriate system of coordinates, x and y, horizontal and vertical. It's obvious that the object is not moving, but we can put it in a mathematical form. Well, there are no forces along x, which means there's no acceleration along x. Because remember, force is mass times acceleration. If the force is 0, the acceleration is going to be 0. And if the acceleration is 0, the speed is going to be constant. Well, if the speed was 0 at the beginning, it would be 0 at the end. Constant, but 0. So the object obviously will not move. Something similar happens along y. The object is not moving along y. Even after it starts moving along x, it will not move along y. So the net force along y is 0. Because the acceleration is 0. So here, if you want, we do our reasoning in reverse. The speed along y is 0. Even if the object eventually starts to move, it will not move up or down. It will move to the right or to the left. So the speed along y is 0 and constant. Therefore, the acceleration along y is 0, which means the net force along y is 0. What does it mean? It means that the two forces along y must cancel out. So N is equal to W. Now, I'm applying a force. Let's ignore this force here for a moment. Fs. And it's not there. I'm applying a force. But the object is still not moving. I can see that. However, now it seems to be a conflict, a contradiction. I have a force, but I still don't have an acceleration. Why don't I have an acceleration? Exactly like before, the object is not moving. So I have a force, I'm trying to cover the force of friction. I have a force F, and I have an acceleration of 0, which means the net force must be 0. So this is this apparent conflict. There is a force, on the other hand, the net force is 0. How can I reconcile the two? Well, by saying there's another force pointing to the left that cancels out this force. And this force we call static friction. Well, we call it friction because it is due to the microscopic interactions between the atoms of the two objects. So it is the interaction between the atoms close to the surface of the block and the table. This is friction. And it is static because the object is not moving. Because these two surfaces, the block and the table, are not moving against each other. So we have a force of friction, although there is no motion. So friction and no motion. We have to be careful because we are tempted to think that there is friction only if there is motion. Not necessarily. I can have friction even if I have only the tendency of motion. The object would like to go to the right, but it's not. And it's not going to the right because of this friction. So I have friction, although I don't have motion. And because of Newton's second law, these two forces must be equal. Now I'm increasing the force until the object is just about to move. And these are the right words to use here, just about to move. So there will be a minimum force that I need to apply to object for it to move. Of course, if I apply something less, the object will not move. But if I keep increasing the force, eventually the object will start moving. So this force will be minimum. Anything below that will not do anything. On the other hand, the static friction has become maximum. Why is that? Because this is the last moment when the object is not moving. Past this point, I cannot talk about static anymore because the object will move. So of course, static means not moving, like we saw before. Static, no motion. So again here, we remember that static means not motion, not moving. However, if I apply a greater force, the object will start to move. Therefore, the static friction is gone. I cannot talk about an object moving and at the same time talking about static friction. The words moving and static don't go together. So when I apply this minimum force, the static friction has reached the maximum. These two forces are equal, like before, but now we have an expression for the static friction. For the maximum static friction is proportional to the normal force. And the factor of proportionality is called coefficient of static friction. It is easy to see that the unit of the coefficient of static friction is 1. It is dimensionless because it is the ratio between the static friction force and the normal force. They are both forces, so the ratio is going to be 1. Now, if we look at an example, we have an object on a horizontal surface. The mass of the object is 2.5 kilograms. So because the mass of the object is 2.5 kilograms, I'm calculating the weight right away, 2.5 kilograms multiplied by 9.8 meters per second squared, 24.5 newtons. This is the weight of the object. I also chose a coefficient of static friction of 0.5. Well, I know that the weight of the object and the normal force are equal to each other, which means the normal force will be 24.5 newtons. And because I know the normal force and I know the coefficient of static friction, I can calculate the maximum static friction, mu s multiplied by n, in this case will be 12.25 newton. So what does this mean? It means that if I apply a force between 0 and less than 12.25 newtons, the object will not move. And the static friction will be equal to the applied force. So the static friction itself will be between 0 and 12.25 newtons. So let's see. If I apply a force of 0, or in other words, if I don't apply a force, the static friction is 0. If I increase this force, let's say I apply 2 newtons, maybe I should apply more so we can see the arrows. If I apply 6 newtons, the object is not moving, even if I press start. The object is not moving because 6 newtons pull to the right, 6 newtons pull to the left. If I apply 8 newtons, notice how the static friction increases. If I apply 10 newtons, maybe I should press start just to be sure, but the object will not move. 10 newtons. I can apply 12 newtons. The static friction is equal to the force applied. Remember, we are aiming for 12.25. Let's apply. I'm not saying this applet is going to be super precise. I don't know if we can narrow it down that much, although it does a very good job. So let's say 12.24 newtons. I'm applying 12.24 newtons. Static friction is equal to the tension applied, but the object is not moving. And now, let's see what happens when I apply 12.25. Before I even press start, actually, I pressed start, the object is moving. So let's reset it. Once again, at 12.24 newtons, the object is not moving. At 12.25 newtons, the object is moving. So what happens after the object starts to move? I don't have static friction anymore. I have kinetic. Kinetic goes with motion. So if I go back to my picture, I have the weight, I have the normal force. And now I apply the force, something that is just enough to get the object to move. This is our 12.25 newtons in the example. The object is moving, and I don't know if you noticed on the applet, but we'll go back there in a minute. It's moving with an increasing speed. Because when the object started to move, the static friction is gone, remember. It became a maximum, and then it disappeared because the object started to move. Its place was taken by a kinetic friction, which has the same expression as the maximum static friction, but a different coefficient. A coefficient called coefficient of kinetic friction. And in general, this is smaller than μs. So what does this mean? It means that this force Fk is less than Fs max. But don't forget, Fs max was equal to F min. And I made the point out of drawing these arrows, one longer than the other, while before they are equal to each other. Well, if I have the force F mean pointing to the right, and I have force Fk pointing to the left, but F mean is greater than Fk, that means I have a net force pointing to the right, which will be F mean minus Fk. Well, if I have this, if I have a net force, I have an acceleration. So in general, I can say the applied force minus the force of kinetic friction is equal to mass times acceleration, or the acceleration is F minus Fk divided by N. Now, for example, for our example here, the force was 12.25 newtons. The mass of the object was 2.5 kilograms. The normal force was 24.5 newtons. So the acceleration will be 12.25 minus the coefficient of kinetic friction was 0.4. I'll show you back when we go back to the applet, you'll see. Minus 0.4 multiplied by 24.5 and divided by 2.5. This would be meters per second squared. So 12.25 minus 0.4 times 24.5, 2.45, and divided by 2.5. This will give us an acceleration of 0.98 meters per second squared. So if we go back to our applet, we should bring the object back, who knows where it is. Coefficient of kinetic friction is 0.4. So indeed, if I start, it has an acceleration of 0.98. But keep an eye on this, though. Keep an eye on it. Look at the acceleration. If the force that I apply is not enough, the acceleration is 0. Let's go to 12.24. Remember, look, the acceleration is 0. And I have static friction. But the moment I switch from 12.24 to 12.25, the acceleration has jumped to 0.98. What happened? The static friction has been replaced by kinetic friction, and the kinetic friction is smaller than the maximum static friction. Where does this speed come from? Well, our kinematic equations. The object is starting from rest, so the final speed will be 0 plus 0.98 times t.